Hello, humans.
Oh, try to sneak in one last throat clear.
Just as I go live, of course.
Yeah,
Yeah,
stupid allergies.
yeah. So we're both suffering over here, y'all.
It's all right.
Do
I'm
you,
hopped up on Claritin. I got
does your
all kinds of
property have bulbs that you discovered with the spring?
uh a little bit, but we planted a bunch. We've got a couple
Okay.
of native. What are the native flowers that we have? The bulbs, irises. That's
Okay.
it. Yeah, we have native irises.
That's awesome.
Yeah. They're just little guys, and they're
Yeah,
they're only about this tall, and they make these tiny little flowers.
we have the
And
same.
the native irises,
Yeah. Well,
yeah,
ours are probably a different subspecies, but yeah, we have native ones. They come up in our lawn everywhere. And so for the first couple months, it's like our lawn is because we don't use anything on our lawn. Our lawn is this fabulous mixture of irises, wild
right.
strawberries.
Probably
Uh,
crocuses. I bet you're getting crocuses.
no, we have crocuses that we've planted on purpose. These are
Hmm.
little tiny irises.
Okay. Cool.
So
Someone's
yeah.
saying that there's a loop. Is there an echo possibly? I don't know if anyone else can confirm but oh nope, never mind. They retracted their message, so
Okay.
everything's fine. Yeah, it's tough. We're still like because the land was so brutalized.
Yeah.
There's regions that have not been planted, like they were scraped clean, and nothing's really been done to them now for like 2 years, 3 years now, and still there's like nothing growing. Like
Oh
slowly,
God.
some plants are trying to expand out, and then the parts we've been putting a lot of our energy in are starting to recover. But we're looking at like 10 years before the soil health for just like the open field area is will support more complicated things than just grass and invasive weeds. And
So
right now, like we even like I'm fine with the invasive weeds because they help build
yeah.
soil. Yeah.
One of the nice things that like I can go to the local garden store and get is like a 5 pound bag of wildflower seeds that are like
Hmm.
the local wildflowers.
That's
And
cool.
you just scatter it the same way you would scatter grass seed. And
Yeah.
then you end up essentially with a meadow.
Yeah,
Yeah.
it's really tricky here. Nobody does that. It's all invasive
Oh, God.
wildflowers, right? So we're trying. I mean, not invasive, non-native. So like
Yeah.
we're trying to only like, except for my garden, we're planting the whole with only native plants, and we're having to build our own wildflower mix
Oh,
that we're going to try
jeez.
to lay down. But also, the soil is so bad that they just don't take very well by soil. I know where you are. I'm sure the soil is kind of incredible,
Yeah,
right? So
yeah. And we've made it better by putting down bark mulch almost every single year.
yeah, yeah,
Um, yeah.
yeah.
So what we'll do, um, just because otherwise things like um, asparagus grows like grass here, but it will get completely overcome by actual grass. So
Yeah.
I'll put down a thing of cardboard with no tape on it, and then pile that in bark mulch, and the cardboard completely decays into the ground. But
Mhm,
it
mhm.
acts like a weed barrier for the 1 year I need it so that I can get to my asparagus
Right,
and other
right.
plants like that.
Yeah. Yeah, no, so I've got years of, but I have to sort of think about it at an industrial scale. So
Yeah.
like I'm planning on maybe buying a wood chipper and then just
Yes.
spraying wood chips because got lots of nice trees that could be wood chipped, and then
Hmm.
spraying the chips out onto the field, and they'll start to break down and add to the soil health. So anyway,
Yeah.
it's a pretty big problem, and we're trying to come up with some solutions. And I don't want to just dump fertilizer and stuff down on it. So
Yeah, one thing to think about, the barn I used to work at, we had some locals who would come by in the summer and just fill up a truck with wood
mm,
shavings and horse poop.
Yeah, for sure.
And that's like
It's a
kind
slope.
of perfect.
Yeah. Yeah, the problem with that
Hmm.
is that you get invasive grasses and stuff through their feed
Oh,
that
right.
could make the journey, and so you're sort of planting your entire field with whatever the horses are eating. So
And we
it's a
grow horse feed where I
problem.
live, so that's less of a concern.
Yeah, absolutely. Um, all right. Should we do the show? You ready?
Probably no, but sure. Um, I'm just like, my left eye is just tearing. I'm sure I'm going to
Yeah,
sneeze 3 or 4 more
yeah,
times. And
yeah. Hopefully, our
yeah.
editors will remove the sneezes.
Oh my goodness.
Yeah.
Okay, I'm going to press record on my audio. Oh, and it's like, what episode are you doing? What episode are we doing?
Uh,
6.
636. Yeah.
Okay, I'll go with that. Okay, so there's that. I'm pressing record on the video.
Okay. Let's press and record.
I think we're ready.
Okay. Astronomy Cast, episode 636, Blowing Bubbles in Space. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, is Dr. Pamela, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing as good as one can do when spring is in high pollination. I'm having fantasies of being out in one of these vacuous bubbles in space where
Right,
there are no
where there's no
trees.
pollen.
Yeah, yeah.
Pollen, yeah. Yeah, again, every year it gets a little worse for me. Every year as allergy season arrives, I have to remind myself that that I do suffer from seasonal allergies because I didn't when I was younger and now I do, and
Oh.
to just take my Claritin and move on. So yeah, but I definitely am a little gurgly right now. So
We
yeah.
apologize for any sniffles that make
Yeah.
it through to the final recording. We're sorry,
Yeah.
folks.
We're counting on our editors to clean up the final audio. So
Yeah.
hopefully it'll be better. All right. We think of space as a vacuum where let me do this again. We think of space as a vacuum, but there are regions of different density. There are winds blowing from stars and other objects that clear out vast bubbles in space and look absolutely fantastic in pictures. And they might have been critical for Earth to even exist in the first place. And we're going to talk about it, but it's time for our break. And we're back. So we're recording the show right now, and I've set one of these bubbles. I think that's the bubble nebula, but one of these incredible bubbles in space, and
Yeah.
many of them have been seen before. And so hopefully people are sort of remembering these cool photographs from like the Hubble Space Telescope that really looks like a bubble, like someone has blown a soap bubble in the middle of space. What is it?
So they are a variety of different things. The one that is behind you, the one that I'm currently showing up on the screen, these are what are called H2 regions. That means they are areas where hydrogen has been ionized, that a little electron has been heated up and flown away. And these regions are created by extremely hot stars giving off ultraviolet ionizing light that over the distance where that light is intense enough to ionize the hydrogen, you get these amazing spheres of glowing gas. And the reason they look like bubbles is these spheres, we see the thickest amount of the sphere around the edges. So that's where, we see these cool red areas.
So the area that is the bubble
Yes.
is, so I had to sort of imagine that you had like the solar winds and the radiation was pushing material away from the stars, but you're saying that the intense radiation from the star itself is ionizing the hydrogen in this area and causing it to glow in a way that's different from the I guess, the background nebula?
So it's a little bit of all of the above,
Okay, okay.
and looking at regions like the Helix Nebula, which is formed from a variety of different hot stars, where you can start to see the structures. What you have is the winds from the hot stars are pushing material out. The ultraviolet light from the hot stars is creating that ionizing radiation that is creating glowing spheres around the stars. So
Right.
you have regions that are glowing brightly due to the ionizing radiation, and you have these filamentary structures that are created by the winds from the stars.
And I guess, what are the implications? Like, you've got a young hot star that is blowing out this intense radiation. What happens to this region around it beyond it looking pretty in our telescopes? Um, like, does it stop star formation? Does it cause extra star formation? What does it do?
So the awesome thing about this is really big blobs of material collapse the fastest, form hot stars that create all of this amazing structure as the first thing that gets created in a star forming region. Once these hot stars are out there doing their bubble blowing thing, blasting out the material around them, they can shock other clouds of material to collapse and form additional solar systems. So this is part of a chain reaction of star formation that just starts with something knocking on the side of a giant molecular cloud, getting that biggest thing forming, and it just all collapses down from there.
So you've got these stars, they're blowing out these winds, they're causing overdense regions out at the limits around them. And those overdense regions are still, I guess, cold hydrogen. And so they can
Yes.
start collapsing into new stars. And eventually you're going to get overlapping stars blowing their bubbles, and you're going to run out of material that is capable of collapse.
Exactly. And when we look out at regions like the Horsehead Nebula, the Pillars of Creation, those not bubble shaped areas are the remnants of material that got knocked around into the shape they are through the combination of massive stars pushing out and then the gravity of what's inside of them pulling in.
Like, when you look at the Pillars of Creation and you see those tentacles, like a
Yeah, yeah.
tentacled hand reaching up, um, and you can see other examples of these same kinds of nodules. It looks very familiar, very similar to what we talked about, these other bubble nebula, but the things are kind of enshrouded in gas and dust, so we can't really see what's going on inside of them.
Those are just protostars. So when they're still enshrouded like that, those are either proplyds, protostars. It all depends on what stage in their evolution they're in. And they haven't fully ignited. Their nuclear reactions haven't fully turned on yet. And so they don't have that light pressure to push everything out from around them. Over time, those pillars are going to get eaten away by the light of the stars forming inside of them. They are literally going to cannibalize themselves to form new stars.
And then we would see the bubble.
Then, well, it depends on how much material is left around and what the shape of the material is. So I have to admit, I've picked and chosen which H2 regions to show you because these happen to look like bubbles. What's amazing about the H2 regions is as you get different pockets of star formation, you can end up with these incredible filamentary structures of the pockets colliding together to blow a series of bubbles that you get more of a froth in that kind of a situation.
It's amazing to me that all of this is essentially driven by gravity.
Yes.
That gravity is what triggers the star formation in the first place, that the gravity pulls in these stars into denser and denser regions, or pulls the gas and dust into denser regions, which turns them into stars. And then the stars, because of their gravity, ignite with their fusion and then are pushing out, with the radiation and their own stellar winds that are causing gravity to make other parts collapse down and continue this cycle. Like, and this isn't necessarily what has to do with today's episode, but literally gravity is just writing the rules of the whole universe.
But light is the other side of this, and that's the thing that always gets me, is our universe is a balance between gravity pulling things together and light pushing things apart.
Yeah.
Stars support themselves in light. Our solar system is largely protected from the interstellar medium by the bubble that our own sun has cleared out around us. It's light versus gravity.
Right. So that actually transitions into the next part of this conversation that I wanted to have, but it's time for another break. And we're back. So you were going into this idea, and I had sort of mentally wanted to cover this as well, is that, when we look at these beautiful bubbles, nebulae, they're young stars, they're hot stars.
Yeah.
But we've got spacecraft out there examining the bubble that the solar system, that our own sun, 4.5 billion years old, is continuing to blow.
Yes. And so here it's our solar wind is the driving process, and it is thin enough and at a temperature where it's not really something that we can go out and just look at. But as the Voyager probes have gone on their escape trajectory out of our solar system, they've been able to see the kinds of particles that they're experiencing, the kinds of fields that they're experiencing are varying on their journey outwards, so that now they're starting to see more and more and more interstellar medium as they leave that protective bubble.
And I mean, I guess like every star has one of these bubbles, and you call it protective. Like, what is this protecting us against?
There's a lot of high energy particles out there that get somewhat deflected, and radiation is really just not a good thing for the human body. So I think it is safe to say that less cosmic rays is always a good thing. Yes.
So it's like we have, like, the Earth has a magnetosphere, and then the solar system has a magnetosphere.
Exactly. And there's, beyond the magnetosphere, literally the solar wind is pushing out and moving the material around this. And while we don't get to see this with our own solar system, it's the kind of thing that we've had the opportunity to see in other systems. V838 Mon is my favorite example. This star, for unknown reasons, let off 2 different flashes of light, and a flash of light has a width to it. And as these expanding bubbles of light with width move away from the surface of the star, they are illuminating the structure of the material around the star, allowing us to see that bubble that has been cleared out by the star's solar winds in the past, and perhaps even enhanced through mass loss of that star.
Oh, that's crazy. Yeah, it's one of these dramatic images, and especially because it's a sequence that Hubble has been observing this star for decades now. We can actually see the light echoes moving through this region. We can see how the shape of the bubbles that it has blown out are changing over time. It's unbelievable that, you sort of imagine things to work at astronomical amounts of time, and yet every now and then there are these things that are unfolding in front of us in vastly faster time periods.
The speed of light, literally the speed of light.
Literally the speed of light. Now, we've talked about young stars creating bubbles, but as stars die, they can as well.
Yeah, and this is where, on the low energy side of death, we get to the planetary nebula. This is the ultimate fate of our own star, and it's how a lot of stars out there are going to well, eventually end their lives. What happens is the outer layers of the star during its red giant phase and beyond get let go as the star expands and the material goes past the point that gravity can hold on to it. We don't fully understand the pulsation mechanism of these massive stars, but stars like Myra can breathe in and out over the period of roughly a year in a rather irregular manner. And on the way back in, they don't always bring everything with them.
I'm sort of imagining you've got this star that's pulsing, and like the mirror variables, the scale to which they pulse is mind-blowing.
Yes.
That they can change from their brightness and their size. Like at one point, they're way out beyond the orbit of, say, Jupiter, and then the next moment, or weeks
Several
later,
months
they're now
later.
down. Yeah, months later, now they're down vastly smaller, and then they do this again at a very regular rate. And I guess each time as they're expanding outward, they're accelerating this material away from the star, and then the star stops and pulls back in, but a lot of that material is still coasting away from the star on an escape velocity, and so you get these just shells of dead star, of sloughed off into space around the star.
And exactly how they get sloughed off is going to be determined through a combination of what stuff is inside that solar system that can block the expansion of that material. So you can end up with systems that have areas that clearly have less material or more material within them. Planetary nebulae are something we're still working very, very hard to figure out because they come in detail where the more and more and more resolution we get on our telescopes, the more crazy structures are revealed in these planetary nebulae. These structures...
Oh, go ahead.
These structures are that combination of a star getting puffed out by light pressure, coming back in as best it can, and just letting go of the light eventually as the core just stops producing more energy, collapses down to become a white dwarf. Now, the star that was expanding and contracting is doing this in an irregular manner. It's doing it while gravitationally interacting with perhaps a binary star, perhaps planets within the system. It's doing it while having whatever interstellar media is surrounding it. And to understand the structure, we have to understand what was there in the first place, what influences might have changed the symmetry of the stellar wind, and everything inside that might have been adding that little extra kick as perhaps a massive planet went past.
Right. Like it seems like the magnetic field of the sun, perhaps the interactions of the planets, these all play part of the mix to create the planetary nebula. And it's still like, we don't even know if the sun is going to turn into a planet. Like maybe the sun doesn't have the right raw ingredients to create a planetary nebula like we see out there, or maybe it does. It's funny that it's used to be assumed and now it's a bit up in the air.
I still remain firmly in the camp of it's going to be a planetary nebula.
You just want one.
Yeah, I do.
Yeah.
It may not last very long. They don't all last the same amount of time, but
Now we talked about this is the low energy version of blowing bubbles as stars die, and in a second we're going to talk about the high energy version of that. But it's time for another break, and we're back. All right. So what happens if we need a bubble and we need it fast?
Best way to do that is to just explode a giant star. Just explode it. It's going to release a massive kick of energy that is going to include remaindery bits of the former star and Also collide with violence into any surrounding material and shock it into doing its own glowing kind of thing.
I think my favorite example of this is the supernova 1987A, which was really the closest supernova that has
Yeah.
been recorded in modern history
Yeah.
while we had really good telescopes. And you can see this debris cloud again year after year expanding outward with
And
blobs
it's
of
a
fiery
figure
material.
eight.
Yeah, yeah.
It's there's a central bit and then these two expanding rings that there's literally a dumbbell of shockwave out there.
And this ties back to the first part of the show when we were talking about how you've got some triggering event that causes the collapse of star formation in a nebula in the first place. And it's often these supernovae, these bubbles, are the
Yeah.
ones that actually get the whole process rolling.
And they can be amazingly energetic events that are giving off gamma rays, X-rays, ultraviolet light. They are heating the area around them. They are shocking them and compressing the gas around them. And if one of these goes off near a giant molecular cloud, it can be just enough force to set that giant molecular cloud out of balance between gravity in and just gas pressure out. So the nudge of a supernova is thought to be part of what triggers this entire process in the first place.
That's interesting when you sort of imagine that you've got like the supernova first is just a big shock to the system that begins the process, but then afterwards this more gentle roiling star formation continues the process until all of the fuel in the solar nebula has been used up. It's absolutely fascinating to think about.
And it's really this bubble blowing process that seems to be at the core of moving a whole lot of things around. So at the very center of our galaxy, our supermassive black hole appears to periodically blow bubbles as well. And these are also shockers that, well, have radio bands and these bubbles giving off high energy light. It looks currently like there are two different sets of bubbles. Again, we have that figure eight structure where something fell to its doom in the center of the Milky Way galaxy, and the high energy light that was given off while the thing was being destroyed blew out bubbles in the interstellar medium above and below that black hole, and that too can trigger star formation.
And so this is where I was going to take this sort of next is, we've talked about just stars themselves and fairly small phenomena, but these can exist at this much greater scale. These bubbles blowing out of the supermassive black hole are tens of thousands of light years long. They're enormous.
Yes.
And yet it's weird, or isn't it interesting that they kind of fall, they're perpendicular to the spin of this supermassive black hole that that has something to do with the way its magnetic field is wrapped up around and the way it's rotating, that its material is falling in and then is being thrown out in both directions. And it happened a long time ago. It happened tens of thousands, millions of years ago, and we're still seeing the repercussions. Is it a time when the sun might have been is it a time when the supermassive black hole might have been a quasar, might have been very bright?
I think going all the way to quasar is a few steps too far.
Right.
But it definitely was active at that point. And we see essentially they appear to expand as the shock wave moves through space. This is at a much more energetic level, similar to when an explosion goes off and the sound waves propagate through the air, creating this wind that pushes things out. And the light goes far faster. But then that shock follows behind, and there are some really cool concerts and stuff where you can see the sound propagating through the crowd as they react. And here, what we're seeing is the energy propagating, well, through the galactic region as it travels through space.
Can we scale this up one more notch? Do we see bubbles at galaxy cluster scale?
I am reluctant to say the word bubble. What we do see in galaxy clusters is the region in the center of the galaxy is extremely hot. It's giving off X-ray radiation. It's that level of hot. But this is gravity pulling everything together and heating it up, not some central dynamo heating it up. We do have jets in the centers of a lot of these systems, but that's different physics that we talked about last week.
Right. So you can definitely get winds at a galactic scale coming from these collisions and interactions and so on, but not necessarily sort of these nice, clean bubbles blowing in all directions in the same way. Well, it's absolutely fascinating and they're wonderful to look at. And now when you see one of those pictures, maybe you'll know a little more about what's going on. Thanks, Pamela.
Thank you so much, Fraser. And thank you so much to everyone out there who makes this show possible week after week. This week, I want to say thank you to a group of our Patreons over on patreon.com/astronomycast. Thank you to Ninja Nick, Janelle Duncan, Michelle Cullen, Mark H. Whittick, J. Alex Anderson, Benjamin Carrier, Frodo Tenenbaugh, Matt Rucker, and Anna User, Shersim, Moose and Deer, Abraham Cottrell, Father Prax, Kimberly Reek, Philip Grand, Mark Stephen Rasnack, Jim McGeehan, Dwight Lillick, Bruce Amazine, Jen Greenwald, Andrew Stevenson, Brent Nearnop, Dustin Ralph, Planetar, GeForce 184, Ksenia Penflienko, Gabriel Galfin, Schmansky, The Mysterious Mark, Rachel Fry, Stephen Coffey, Peter, Sean Matz, Joe Wilkinson, Glenn McDavid, John Usiaf, the Air Major, and Benjamin Davies. Thank you all so very much.
Thanks, everyone, and we'll see you next week.
Bye-bye. And then they saved.
And then they say...
And there was a lot of discussion going on over on Twitch. I'm going to try and figure out what was going on.
Oh, cool. Okay. Or bad. Like maybe there's something on our faces.
So apparently there's a 6-frame long audio dropout that occurs periodically. So Richard, the way that Allie's dealing with it for Daily Space is she's editing the podcast audio and video together using the podcast audio and the video to fill in the weird dropouts that just sometimes occur. Yeah. Okay, I'm just going to rub my eye because allergies. So Veronica Cure asks, are these bubbles moving? So as the galaxy rotates, the bubbles do move as part of that rotation, and then they're also expanding.
Right. Linda Sadiq asks, would an observer outside our solar system be able to see a nebula bubble from solar wind?
I don't think the area around us is warm enough that it would be visible.
So like the Voyagers can detect it because they're measuring just the density of the particles that they're flying through, and the density has slightly changed. Like the Earth's atmosphere is so much more dense than space, but they're getting like just a few more of particles as they're going through, and so that, but you would have to see the radiation coming from the particles interacting with the interstellar medium.
Or the area outside of us would have to be warm enough that it's giving off light.
Yeah. Yeah. So that would be tricky. That's all the questions that I've got.
Okay.
Do you have any questions over there?
No, there's a great discussion going on about the weird audio glitches that are sometimes getting heard.
All right. Doran Smulian asks, can a tidally locked planet maintain a magnetic field? Won't the internal dynamo ground to a halt?
So, yeah, it might have an intrinsic magnetic field that it gets due to interactions with its star's magnetic field. So, when you look at the Jupiter system, which is a good surrogate for that kind of a situation, you can see that Io has magnetic interactions with Jupiter. This is part of what creates that amazing torus. But they're not generating massive magnetic fields on their own.
Well, Ganymede has an intrinsic magnetosphere.
Right, but it's not massive, and it doesn't appear to necessarily be from a dynamo so much as being from interacting with Jupiter's, from what I understand. Now,
Okay.
magnetic fields is something that changes constantly.
Right, but I guess I'm wondering, like, what does if Earth was tidally locked to the sun, why wouldn't it still have its own magnetosphere? Like, what does your planet being tidally locked? Like, sure, it only shows one face.
So the
but don't you
magnetic
still have the dynamo going on inside?
So the magnetic field is generated by the rotation of the planet. And if the planet is tidally locked, unless it's super close, it's going to be rotating very slowly and not have the kind of rotation rate to generate a large magnetic field. Now, just like when I was little, my grandma taught me always store your sewing scissors with a magnet on them, and that magnetizes your sewing scissors. So sticking an object in a powerful magnetic field can cause it to have a magnetic field. And so you can end up with that kind of an interaction instead.
So if the Earth was rotating more quickly, would that generate
a stronger magnetic field?
A stronger magnetic field.
Yeah.
Right. And so I guess that's the solution to Mars. Just spin it up until it's like a buzzsaw.
Well, you have to also melty its center a little bit. Now, Venus, if you spun up Venus, you could generate more of a magnetic field.
Right. Very interesting. Jeremy Carrier asks, is the escape velocity for Andromeda the same as the Milky Way?
No, it's a bigger galaxy.
Yeah. See if I can find it.
He's the numbers person. I just remember the concepts.
I'm just Googling. Whoa. So it's 470 kilometers per second, which was lower than an expected value.
What?
So the Milky Way is 550 kilometers a second. And Andromeda is 470. And this was one of the reasons why they dialed down dialed down the mass of Andromeda.
So where is that escape velocity from?
Right.
Because the escape velocity from the center of a galaxy, from 100 megaparsecs out, from each distance is going to change. And I feel like those numbers aren't from the same place.
Well, the density is the key. That like if you doubled the mass of the Earth, the escape velocity would only go up by a little bit, like maybe, and you double and if you doubled the radius of the Earth while you doubled the mass, I think the escape velocity would actually go down because it's all just about the density.
Yeah.
And so with Andromeda, you're going to have this much larger dark matter halo that's pulling in all directions. It depends on the density of where the stars are. And all that. So that's interesting that
I still want to
Yeah.
know more. I still want to know
I
more.
can send you the paper if you want.
Yeah, I feel like if you're at the same distance from both of them, that would change things.
Yeah, so they're guessing at a galactocentric distance of 15 kiloparsecs,
Hmm.
then your escape velocity is 470. Um, and they use that to then change what they knew as the mass.
So that distance is still within the mass distribution of the galaxy. So
Yeah.
I feel like if you were outside the mass distribution,
Yeah.
that Andromeda would have a higher escape velocity.
And Jeremy's saying, so say the escape velocity from the black hole, that changes everything because our black hole is like 4.1
Yeah,
million
yeah,
times the mass of the sun, and theirs is 100 million times
yeah.
the mass of the sun. And so if you're at the black hole, then everything changes. But I don't know what the escape velocity would be to get away from, again, if you're inside the event horizon, the escape velocity is
So
faster than the speed of light.
so what we're looking at is with the two systems, if you're say, I don't know, like 1,000 parsecs from both supermassive black holes. Andromeda's black hole is so much bigger, it's going to be harder to get away from. But as you move out, because Andromeda is intrinsically fluffier than we are, there's
Right.
going to be a point where they have the exact same escape velocity. There's going to be then Andromeda ends up with a lower. But then as you move out and the total amount of mass inside of your distance goes up for Andromeda,
Yeah.
and then flattens for the Milky Way, then the escape velocity for Andromeda is going to go back up.
So it really just
It's
depends on where you're trying
calculus.
to escape. Right.
Yeah.
But the point being, it is order of magnitude roughly the same as the Milky Way, which is
Yes.
surprising considering the fact that it is more massive than the Milky Way.
By
And
like
that is,
30%.
yeah, well, it keeps getting less more massive than the Milky Way every year that goes on. It's quite funny that, we used to think that Andromeda was dramatically more massive and bigger than the Milky Way, and now it is kind of bigger, kind of more massive. And I'm sure we'll get to this point now where um, that we're going to be at this point where they're like the same.
Okay, so we have two questions coming in from Twitch. First, Keeper asks, why do you want to magnetize your sewing scissors? So that when you spill your needles on the floor, you can use your scissors to pick up all of your needles. Grandmas think ahead.
Right.
And then Cersei asks, isn't a constant escape velocity like equal to the maximum velocity a body could accelerate or something? No. So the way it works is it's a balancing of energy. The escape velocity is the masses end up canceling out. So you have your kinetic energy on one side when you leave the planet, so mv 1/2 mv squared, and then you have your potential energy from gravity, and you want basically the kinetic energy so that everything balances out to zero at infinite distance.
Right.
It's an energy equation to calculate what is the velocity that allows you to overcome the potential energy of the system, which is gmm over r squared. So you have the mass of your object cancels out in both equations, and so you're only looking at that 1/2 v squared equals the gravitational constant times the mass of whatever the heck you're trying to escape over your distance from the object at the point you're trying to escape from. So
Right.
set those equal and you get your escape velocity, and it's all energies.
So I wanted to share an idea that I had, an analogy that I
Okay.
had. I was having this over the weekend, and because when you get these people, they're like, I don't like dark matter. I don't like dark matter.
Yeah, I don't
Like,
like it either, but I
well,
still
who
got to
does?
deal with it.
Yeah, yeah. And they'll be like, like astronomers just made something up. They just
No.
invented some particle just so they can get more funding or blah blah blah, whatever. And I was sort of thinking like they're thinking about it so wrong, and I was trying to think of a way
Yeah.
to explain this. And so here's my analogy, which is
Hmm.
like if a person is like, I don't think dark matter is real, you can say, do you think dreams are real? And they were like, well, what do you mean? And you're like, okay, nobody knows why we dream. So are you saying that dreams aren't real? Because dreams are something that we
Yeah.
have personal experience with. Like we all dream, or most of us dream. And yet humanity has no definitive answer for why dreams happen.
Yeah.
What is the brain doing when it is dreaming? And so to say that you don't like it or you think that it's just being made up is exactly the same as you
Yeah.
saying that dreams are being made up.
Yeah.
And because we have mountains and mountains of evidence, independent lines of evidence. And I think that for a lot of people, when they say, well, I don't like this idea of it being a particle, that's fine.
Yeah.
That's
Think that all
equivalent
you
of
want.
yes, think that all you want. That's like you saying, I don't think that that the purpose of dreams is for the brain to process the information that it gained in the previous day, or it's a form of defragmentation of the brain. Yeah, for sure. People disagree. Some people think that dreams are defragmentation. Other people think dreams are, I don't know, the ghosts of our ancestors speaking to us from throughout history. Other people think they're premonitions and visions for the future. But you've got to agree they're happening, right?
Yeah.
Like, do you
Yeah.
agree that you go to sleep, stuff happens in your mind, and then you wake up the next morning remembering the stuff that happened? It is a experience. And so if you took the same telescope, the same tools and techniques, you could confirm to within high degree of precision exactly what the astronomers are seeing.
Yeah.
And that it's the name, it's dark matter is the thing that is catching people up, because it might not be matter. It could definitely be a misunderstanding of gravity at the largest scales. It could definitely be
I'm pretty sure we're at the it is stuff stage for dark
sure,
matter.
yes, of
But
course.
dark
You can have that
energy
argument.
could be a force, it could be a pressure, it could be
It could be
yeah.
energy leaking in. It could be dreams. Oh, now we've come back full circle. So so now I kind of feel like, whenever someone wants to say, like, I don't think dark matter is real, I'm saying, well, do you think dreams are real?
That
Like,
I'm gonna borrow that, and I think everyone here
please
should
do.
borrow that.
Yeah, definitely borrow, because I think it's such a, like, now they have to, and then you can say, so what you're saying is that because you don't believe in this version, this explanation, this proposed hypothesis for the purpose of dreams, you don't think dreams are real.
Yeah.
That's ridiculous, right? Just because you disagree with one proposed hypothesis for the existence of a phenomenon does not mean that the phenomenon isn't real.
Keeper just said maybe dreams are garbage collection in the simulation.
Yeah, exactly. They could be garbage collection. There could be 1,000 reasons for why dreams exist.
Yeah.
But you've at least got to agree that these things are happening to us.
Yeah.
So, yeah. Anyway, so now anytime anyone says, I don't think dark matter is wrong, I say, do you think dreams are real?
That's awesome.
Yep.
That is really awesome.
That was my my little insight over this weekend, because it bugs me so much.
Yeah.
It really gets under my skin.
Well, so and the other side of that as someone who works in science, that whole to get more money.
Yeah.
Like, we are so underpaid as a function of our amount of education. The idea we don't get rich.
Yeah, you know what would pay better than being a scientist? Anything.
Yeah. Not anything. I mean, to be fair, like waiters and waitresses, especially in this country, there's lots of things that pay worse. We're solidly
post-grad make.
Post-grad starts, depending on where they are, 45 to 65K.
Okay, what about a grad student?
Grad student, you're making like 14,000 a year.
Yeah, you're making 14,000. So you're a scientist.
Mm-hmm.
You are. There is one field that you know more than anyone else.
Yeah.
On planet Earth, and you make about $1,000 a month, $1,200 a month at most.
Yeah.
That's madness.
And
that is.
And a lot of places do pay less than that.
Yeah. And so it's crazy the
Yeah.
how to make that argument that scientists are just like trying to get paid. And then the other thing is like scientists don't care about the outcome. Like climate scientists are going to be busy no matter what because
They
there's
care
lots
about
of
the
things to
outcome
study in the
because
climate.
some things make them want to reproduce less than others. The
Yeah.
number of people who understand climate change in my life who have children is very tiny.
Sure. Yeah, of course. Yeah, you're going to get to a point where you understand the repercussions of the science that you're studying.
Yeah.
Like people who study dental decay bacteria, they might brush their teeth really well.
Yeah.
But then doctors smoke, so who knows? Right? Doctors and nurses often smoke.
I think that's just fatalism.
Yeah. Yeah.
If you want someone who's going to have a DNR, it's going to be a medical professional because they know the consequences.
Right. Yeah, maybe so. But yeah, anyway, it is pretty funny. I think I've been like cleaning up the spam on my Facebook page, on the university Facebook page, and this has put me into this state where people just like make just this casual crappy comment,
Yeah.
and it really like I want to understand like what's wrong, who hurt you
Right.
that
Right.
you feel the need, like you spend your day on Facebook reading things that you vehemently disagree with and make
Yes.
snarky casual comments. Like this is your life.
Yeah.
Sucks to be you. Who hurt you? Like this is it. This is your aspiration. This beautiful world life. This is what you choose. This is how you're going to spend it. And then you're going to die. Anyway, yeah. So that's where my mind is at. It's just like, and so I am categorizing it.
So I'm going to make things more cheerful because Twitch has now totally ruined my brain.
Mm-hmm.
Rich is doing phenomenon, do 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 do, phenomenon, do 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 do. So may you now have that in your head too.
Thank you. Phenomena. Any more questions? Oh, wait. Ben Kalo asks, I read Stratolaunch is now in the hypersonic testing business. Thoughts? Who are customers? No more orbital? I hadn't heard that.
I hadn't either.
I heard that Stratolaunch had done a recent test. Let me see. The future of hypersonic testing. Yeah, you're right. I mean,
Okay.
yeah. Okay, so like for starters, who competes against Starship?
No one right now.
Yeah. Yeah, nobody is planning to compete against Starship, which is madness. Except maybe the Chinese maybe are thinking about doing it. Everyone else is trying to compete against Falcon 9.
Yeah, lower hanging fruit. I mean,
Yeah.
I feel like if Blue Origin could get its expletive together, Bezos would want to compete with Starship, but they just don't have their. They
Yeah,
don't have it.
they're building yesterday's rocket with New Glenn. It's madness. Yeah, it's going to
SLS
be
is what makes me sad. I am very sad about SLS. They need to cancel SLS.
Yeah. But I think we've had this conversation many, many times, right? Like, what do? You cancel SLS. No, actually, I think we have solved this. Right? What do? You cancel SLS. You put Crew Dragon on Falcon Heavy.
Yeah.
And you fly to the moon with it.
I mean, their whole idea of having orbital refueling of a lunar starship, so that you launch to a cislunar space station, switch vehicles, and then bounce. I'm down with that. So I can imagine like Crew Dragon to the space station, and then back and forth from the moon on the lunar starship. The issue with Space Launch Systems SLS is like that. First of all, it's like $4.2 billion per launch.
Yeah, it costs all the monies. Yeah.
Nothing is reused. They're currently literally burning through the old space shuttle engines at some point.
I can't even listen. I don't even say those words. Yeah. Okay, but like let's imagine that there's some fatal flaw with Starship. It
Hmm.
can't work. It won't work. It'll never
Yeah.
work. Now, I don't think that's true. I think it's going to absolutely work, and we're going to see this thing take off and land, and everything's going to
Yeah.
eventually work out well. But let's imagine there's some fatal flaw that literally you'd have to violate the laws of physics. Could you do the Artemis mission without Starship and without SLS? I think so.
Yeah.
Yeah, you launch to the Deep Space Gateway
Hmm.
on a Falcon Heavy carrying Crew Dragon.
Hmm.
You have additional landers brought to the station using other Falcon Heavies, and astronauts go up and down from the moon to the
Yeah.
station and back to Earth in Dragon.
Yeah.
So it's all feasible without SLS.
Yeah.
And SLS is only going to be carrying the Orion capsule to the Gateway. Like, it's not carrying a full stack lunar lander system all the way down to the surface of the moon and back to Earth. Yeah. And it's just like the writing's on the wall.
So I have so many issues with SLS, so many issues.
Yeah.
Starship is using iterative design. They know they're going to blow stuff up as they figure out the right way to do things. With SLS, they gave themselves one chance to get it right.
Yeah.
One design, and that's it. And I just don't. I mean, anyone who's ever built anything, you know, you want to rebuild it and make it better. And at a certain point, you're like, I've learned enough. I want to throw everything out and start from scratch. And Starship does that.
Sure. But again, remember my assumption, fatally flawed, can't work, laws of physics prevent it. What if there's
Then we still have
still
Falcon Heavy.
a vastly cheaper scenario that you can follow?
Yeah.
And it would maybe increase the launch cadence of Falcon Heavy and figure out how to make that work even better and more smoothly and so on and so forth. So yeah, no, I mean, like if Falcon Heavy didn't exist, well, you could still do it on a Titan or a Delta Heavy, like, or an Ariane Space.
Aren't the Delta
6.
Heavies retired?
Sure. And don't the Atlases rely on Russian engines? Sure. So man, SpaceX is just gonna run away with this whole thing.
Well, and I hadn't realized that so many of ESA's rockets were relying on Ukrainian technology.
Yep.
And that plant no longer exists.
Right. Yeah.
So, yeah.
All right. Well, we've reached the end of our hour.
Before we go, folks, next week, Europe is changing times. No one knows when anything is, but we will be a different time next week if you're in Europe. The rest of you are on your own.
Right. As you always are.
Yes.
You know when savings time is here to mess up your schedule. All right. We didn't even have that argument about whether we'd prefer daylight savings time or standard time. We'll talk about that later. Pamela, what are you working on? Where should people go find out more?
I'm doing so many different things. Right now, I'm actually focusing behind the scenes on writing a kid's book with my best friend. And so if I'm a lot quieter, it's because we're looking at the illustrations coming in from the illustrator and going, oh, that's fascinating physics, and trying to get everything perfect. But beyond that, we have the Daily Space, Tuesday through Friday on Twitch, same time as Astronomy Cast is here on YouTube and Twitch. Come check it out, and we will tell you what's new and awesome in brief. Then go to YouTube and learn it in depth.
I've got
YouTube, Universe
latest
Today.
question show. Oh yeah,
Sorry,
that's a great website. I like it.
Meant to plug you.
Thank you. I've got my latest QA coming out in a few hours, and then another live show tonight. So come join me on my YouTube channel. All right. Well, thank you everyone for hanging out today with us. Thanks, Pamela, for bringing the brain. Thanks all the moderators. Thanks everyone on YouTube and on Twitch, and thanks as always for behind the scenes efforts from Nancy Graziano, all the editors, all of the producers, and this incredible team that makes the show continue to happen week in, week out. year
Yeah.
in, year out, decade in, decade out. Thanks, everyone.
Yes.
And we'll see you next week.
Okay. Bye-bye, everyone.